I want you to consider a simple scenario. You push a sack of rice off a balcony. It falls for 2 seconds, and at the 2-second mark, it hits the ground. Let's make a simple model for the velocity of this falling sack of rice. If we push it off the balcony gently, its velocity while it's falling can be modeled as 9.8 times the number of seconds it's been falling. So at 0 seconds, its velocity is 0. At 1 second, its velocity is 9.8 meters per second. And if it were still falling at 2 seconds, its velocity would be 2 times 9.8, which is 19.6. However, it's not falling at 2 seconds. At 2 seconds, it hits the ground. So let's say starting at 2 seconds, its velocity is 0. Now this might not give the exact velocity of the sack, but it's a good enough model for us. So here's a question that I want you to think about for a second. When is the sack falling the fastest? In some sense, this is kind of a difficult question to answer because it's falling the fastest just before it hits the ground. So here's a similarly difficult question. How fast is the sack going at its fastest? In our model, it doesn't quite reach 19.6 meters per second because 19.6 meters per second is how fast it would be moving if it were still moving at 2 seconds. But it gets sort of close to 19.6. So here's something we can say. As time is increasing and time gets closer and closer to 2 seconds, the velocity gets closer and closer to 19.6 meters per second. So this starts to sound like something we can express with a limit. But the sticky thing is we're only looking at this from the left side of the graph. When the sack hits the ground, everything's going to change. So what we're going to do is we're going to write the limit as t goes to 2, but we're going to write the 2 with a little minus sign. We read this as the limit as t approaches 2 from the left. And it means we're only looking to the left of t equals 2. We're ignoring what happens to the sack starting at 2 seconds. We're ignoring that right-hand part of the graph. I want to make 2 observations at this point. The first observation I want to make is that in our model, the velocity of the sack at 2 seconds is 0. It is not 19.6. Remember, when we take the limit of a function as t goes to 2, we don't actually care what the function is equal to at 2. The second thing I want to observe is that the limit of the velocity as t goes to 2 does not exist. Remember, for a limit to exist, a function has to approach a single number. But if we look to the right of the graph, as time gets closer and closer to 2 from the right, the velocity remains at 0. So since this function is somehow approaching 0, as t goes to 2 from the right, but somehow approaching 19.6 as t goes to 2 from the left, the limit of the function as t goes to 2 does not exist. Now that you've seen a limit from the left, I want to leave you with a final question. How do you think this expression should be evaluated?